Good. So let's continue. Um, so let me go to the page. So we have a non-empty set of real numbers bounded above. Those are the properties we need for us to know that the supremum exists. Okay, and given that, we define this set, the set C plus A, which means for every element in capital A, we're going to add the number C before it. Okay, so you get a new set, which is essentially like a translation of the original set, right? We're moving that original set C units to the right or to the left, depending if C is positive or negative. So it kind of makes sense that this property holds. If we want to do the supremum of this new set, well, it should be the supremum of the previous set plus C, right? You just take the supremum and you move it C units, either to the right or to the left. But we want to do this with a little bit of more care to show how you can actually prove these types of things. All right, so here comes the proof. So we need to show that this set, so first of all, we don't even know if this set has a supremum. We need to check that it is non-empty and bounded. So let's give a name to the supremum of A. So let's call it S. Let S be the supremum of A. So now what I need to show is that C plus S is, so this is what I need to do. I'm gonna put it here, need to do, be my on the side, and I need to check that C plus S is an upper bound of C plus A, and also that C plus S is the least of the upper bounds. Okay, is it working now? Yeah, okay. So this is what we need to do. All right, so let's start with the first one. Why is C plus S an upper bound of this set? Well, that's easy because S is an upper bound of A, right? By definition, because S is a supremum, so we know S is an upper bound of A. The meaning of that is that S is less than or equal little a for all little a in capital. All right, so we know that. Then all we need to do is add C to both sides. And then what we get is that C plus S is less than or equal A plus S. Upper bound, sorry, my bad. It should be the opposite inequality. Okay, let's hope this works. So like I was saying, to show something is the supremum, you need to show two things, that it is an upper bound and that it is the least of the upper bounds, okay? So this establishes that it is an upper bound, so this C plus S is bigger than any of the numbers A plus, should be C plus A, right? We're adding C both sides. So now all of these numbers C plus A are less than or equal C plus S. So this establishes that this guy is an upper bound, plus C plus S is an upper bound of the set C plus capital A. Good. Second part is to show that it is the least upper bound. All right, so let's pick another upper bound. Now for the second part, suppose that B is an upper bound of C plus capital A, right? What is the meaning of that? Well, it means that this guy is greater than any element in here. This means B is greater than or equal C plus little a for every little a in capital A. Right? Okay. So then what I can do now is subtract C to both sides. And this is what we have. We have that B minus C is greater than or equal A, again, for every little a in A. And that means B minus C is an upper bound of A. Of capital A. It's an upper bound of capital A. And because it's an upper bound, it has to be greater than the least upper bound. And greater than the least upper bound. Thus, B minus C is greater than S, because S is the least of the upper bounds. And then all I need to do is add C again. And then what this is telling us is that C plus S is smaller than any of the upper bounds, right? Remember, we started with an arbitrary upper bound, and I just show over here that this number S plus C is smaller than that upper bound. And S plus C is an upper bound itself. So this means S plus C is the least of the upper bounds. Hence, C plus S or S plus C is the least of the upper bounds of C plus A. That is, C plus S is the supremum of C plus A, and that's what we wanted to prove, right? Remember that S standard, it was just a placeholder for supremum of A. So this is C plus supremum of A. All right? Okay, so that's a little example that I wanted to show. And then we also have a property that is quite helpful to show supremums in general. And this is lemma 1.3.8. It says, assume S is an upper bound.
Professor, can you show the last line that you have on the last paper?
Sure. Put it right here on top. All right, so this lemma says, suppose S is an upper bound, then it's a way to check when something is a supremum. It says, then the supremum of the set A is S, if and only if, for every epsilon, there is A such that S minus epsilon is less than A. So in other words, something is the supremum if it has the following property. It's an upper bound. Let me make a picture to explain this. It will come better with a picture. So say we have a set A here that is, I don't know, maybe a segment, and then some dots here, I don't know, and some other dots, so something like that. That's my set S, A, I mean. And then this is what this is telling you. How can you tell if something is a supremum? It's essentially the same as the definition, but I find this sometimes works better for you guys. It's intuitively easier to understand for some reason. What is saying is the following. You have to have an upper bound. So it has to have an upper bound with the following property. If you move a little bit to the left, if you move epsilon to the left, you capture someone in A. So this one obviously does not have that property, right? Because here, if I jump a little epsilon this way, and I look at S minus epsilon, I didn't catch anyone here, right? I didn't have any A's to the right of this point here. So that tells me that this guy is not the supremum. Ah, but if you pick this one here, then it works, right? If I pick this one here and I move a little bit to the left, doesn't matter how small I move to the left, I'm gonna capture a blue dot. And then that makes me the supremum. Make sense? It's a very useful lemma when it comes to proving what is the supremum of specific sets. So let's go over the proof of it. It's actually a somewhat straightforward proof as well. Here we go. So it's an if and only if statement. So there's two things we need to show. We need to show that if it is the supremum, then it has this property, and that if it has this property, then it is the supremum. So let's start assuming is the supremum. So we're going in this direction in the if and only if. So suppose S is the supremum, okay? And then I need to show that this property happens. So let's pick an epsilon, pick epsilon greater than 0, and consider S minus epsilon, right? So what do we know about S minus epsilon? Well, we know it's smaller than epsilon, right? Clearly, S minus epsilon is smaller than S. That's what I meant. I said epsilon, my bad. S minus epsilon is less than S, but S was the least of the upper bounds. So that means S minus epsilon is not an upper bound. So S minus epsilon is not an upper bound. Again, let me explain why that is. If it were, then it would be smaller than the least upper bound. And that's not right. So this guy is definitely not an upper bound. And what is the meaning of not being an upper bound? If you're not an upper bound, then that means there is an element that is bigger than this number. So there is little a in A such that S minus epsilon is to the left of A. And that's what we wanted to prove. Remember, that's the property we want. This one over here. Okay, so now let's go the other way around. Let's suppose we have a set that is an upper bound.
I think you meant it would be greater than the least upper bound.
Where?
If it were, then it would be.
It would be smaller than the least upper bound, is what I meant, right? See, over here, S minus epsilon is less than S. So if this guy was an upper bound, then because it's smaller than S, it would be smaller than the least upper bound, and that's the contradiction, right? That's why.
Oh, I see what you're saying. Sorry.
Okay, no problem. I'm happy that you get it. That's much better. So please always ask your questions. That's very important to understand it. Okay, on going backwards now, we're gonna assume that S is an upper bound. That's an overall assumption, right? Over here at the top, we know that S is an upper bound. So we're gonna suppose S is an upper bound for A, and it has a property. And for every epsilon, there is some little a in A such that S minus epsilon is smaller than A. And then what we need to show is that S is the supremum. Now we already know it's an upper bound, so the only thing we need to show is that it is the least of the upper bounds. So let's pick another upper bound. So let B be an upper bound of A. And suppose B is smaller than S. So suppose it's not, right? So we want to show that S is the least of the upper bounds. So if it's not the least of the upper bounds, that would mean there is some upper bound that is even smaller than him. Well, if that happens, let's now consider as epsilon this distance, the distance from B to S. So S minus B. And if we do that, then by this property, over here, there is some A such that S minus epsilon is less than A. Well, what is S minus epsilon? Well, here's the definition of epsilon. So it's S minus B. And if you cancel the S's, this will tell you that this is B. All right, so this is what I got. I have, by using that epsilon, I show that B is less than A. But that cannot be. We started with an upper bound of A, right? This is a contradiction because we said that B is an upper bound. This contradicts the fact that B is an upper bound of capital A, right? We should say capital A. Okay, so a contradiction to what? To this supposition that B is less than S. So therefore, B is greater than or equal to S. And then that means S is not only an upper bound, but it is the least of the upper bounds because it's smaller than any other upper bound. Therefore, S is the least upper bound, which means it's the supremum. All right, and that finishes up the proof of a lemma, the two sides. Good, and we'll come back and use this lemma to show how some specific sets that we've considered before, why their infimum or the supremum is what it should be. So there's of course an equivalent version of this lemma with infimum. If you want it for infimum, then it has to be over here, S is a lower bound, of course, and then it will be the infimum if there is an epsilon, and then over here, instead of being S minus epsilon, it will be that you add a little bit something, and then you catch an element of A. So it's going to be S plus epsilon is greater than A. So you can figure it out on your own. It's actually not that hard. Okay, moving on. We'll go now to the next section, which is the consequences of the axiom of completeness. Consequences of completeness. And some neat things that now we have for the real numbers.
Professor, can you show the last line of the last one again?
Sure. Put it again like this. Consequences of completeness. And the first one, it's something that we're going to use actually for some important things, and it's called the nested interval property. Nested interval property. And this is what it says. It says, for each n, a natural number, assume I sub n is the closed interval an bn. So remember, these are the real numbers that are strictly between an and bn. Okay? Assume in contains in plus 1. That's the nested part. So in other words, I1 contains I2, and I2 contains I3, and I3 contains I4, and it continues on like that. So it's always one inside the other, and there's infinitely many of them, right? There's infinitely many of them, lots of intervals, one inside the other, inside the other, inside the other. All right, and then here's the conclusion. Then this happens. The intersection of all of them is non-empty. Neat, right? So you have a sequence of nested intervals. Let's do a picture. Here's the real line. And you have a bunch of intervals, like say this one, this is A1, from A1 to B1. And inside that one, there's another one from A2 to B2. And then another one, A3 to B3, maybe here. And then A4 to B4, and so on. And I cannot draw many more because you won't see things, but you get the feeling, right? So it's one and another and another and another and another and another, and then this gets super tiny, but you have infinitely many of them. And the important thing is that you're gonna have a point here that belongs to all of them, right? At least one element that belongs to all of them. That's what this property says. Beautiful, very nice property. Okay, why is this true? Proof. Okay, so we're gonna use, of course, completeness. In other words, we're gonna use the fact that the supremum exists if we have an appropriate set, okay? And here's the appropriate set. Consider the set of left endpoints. I'm gonna call it capital A, and it's gonna be A1, A2, A3, etc. So more formally speaking, is the A sub n's, where n ranges over all the natural numbers. Okay, that's the set I'm gonna consider. Okay, now I want to use the supremum of that set. Now, to be able to do that, I need to check two things, right? Is my set A non-empty, and is it upper bounded? Now, this guy is obviously non-empty. Look at all the elements in here, right? So I'm just gonna write it here so you don't think I forgot. Clearly, A is non-empty. Now, why is it upper bounded? And what you can see here is that because of the nested property, right? The nested property means that, right here, by the nested property, we know that that AN is less than BN, right? And then BN is smaller than BN minus 1, et cetera, less than B3, B2, B1, whatever those numbers are. See? In other words, the point that I'm trying to make here is that the A's are smaller than all the B's, right? Look at the picture here. All of the B's are to the right of all of the A's. So by the nested property, every BN is an upper bound of capital A. So every one of the B's is to the right of these A's over here. Okay, so then definitely we can talk about the supremum. So let's give it a name. Let's call it X. Let's call it X. Let X be the supremum of A. All right, and this is my guy. I claim that X belongs to all of the intervals, right? And why is that? So we claim that X belongs to all the intervals. Well, why is that? Well, here we go. First, because X is the supremum, X is an upper bound. That means X is bigger than all the A's. X is an upper bound of capital A, so X is bigger than AN for all N in the natural numbers, right? X is bigger than all the A's. That's the meaning of being an upper bound, right? Well, that's one part. The other part is that it is the least of the upper bounds, right? And we know that all the B's, every B is an upper bound. On the other hand, every Bn is an upper bound of A, and X is the least of the upper bounds. So X is less than or equal Bn, right? For every N. And if you put these two together, what it says is that AN is less than or equal X less than or equal Bn. In other words, X is between AN and Bn. That means X belongs to the interval IN. And because it belongs to all of them, then it belongs to the intersection. If it's in all of them, then it's in the intersection. And because we found an element in the intersection, that means the intersection is non-empty.
Professor, I don't understand. You're saying X is an upper bound of A, but then you're saying every Bn is an upper bound of A.
Mm-hmm.
So I don't get that.
Yeah, so let's go back to the picture here, right? See, so what is A? A are these points. Let me paint them with purple. This is A, right? The left 10 points. That's A. Now, do you agree that all the B's are to the right of the A's?
Yeah.
Okay, so that means the B's are upper bounds, right?
Mm-hmm.
Yeah? Now, X is also an upper bound because it's the supremum. So the supremum is among all the upper bounds, look for the smallest. Yes?
Oh, okay.
Yes? So that's why this guy is an upper bound. The fact that it's an upper bound tells me that it's bigger than all the A's. An upper bound, so X, I cannot draw X because I would need like a microscope, but it's somewhere over here, right?
Can you move your paper down?
Yeah. X would be somewhere in here, right? Among all the upper bounds, you pick the smallest. So X is an upper bound. That's why I have this property. But also X is the least of the upper bounds. So among all the upper bounds, X is the minimum. So, right? So X is smaller than all the other upper bounds. And that's what makes this work, because now X is between AN and BN, and that's what it guarantees that this intersection is non-empty. All right? Did that help?
Yes, thank you.
Excellent. Yeah, so this is a beautiful property. We'll use it later on, many times actually. So we'll come back several times. And then here's another one, and this one is sort of something that you probably don't need. So this is a subtle point. This next one we're going to see here. Maybe it's something that you think we already know, but in fact, like our book argues, it's important that we actually prove it. I'll explain. Let me write it down, and then I'll explain. It's called the Archimedean property from Archimedes. And this is what it says. It says, given, it has two parts. The first one, the second one follows from the first one. So really, the first one is the important one. Given a real number x, there is some natural number such that n is bigger than x. says strictly bigger, not that it matters, but I'm just gonna write it at how it is in the book. And the second one, it says given y greater than 0, a real number, there is again a natural number such that 1 over n is smaller than y. Okay. Now, let me talk a little bit about why this seems like a silly thing for us to prove, but it's important. First of all, let me explain what this means. This is a rephrasing of number 1. What this means is, you give me any real number, and I can find a natural number bigger than that, right? So, in other words, it seems like you can find natural numbers as big as you want. That's what we're saying, right? And then you may be wondering, why do we need to prove that, Professor? Isn't that obvious? Isn't that obvious that the natural numbers become bigger and bigger and bigger, right? And I mean, they approach infinity as you get the n bigger and bigger. So of course you can make them as big as you want. Why do we need to prove such a thing? It's not such a silly thing. And here's the reason. Yes, when we started talking about numbers, if you go back to our first class, the first thing we did was we started with those, with the natural numbers, right? And with the natural numbers, and we did the integers, and then with the integers, we did the rational numbers. Okay? Here is the point. See, here's why we need to show this. Because of the following. What if, I mean, I know it seems far-fetched, but what if by using this axiom of completeness, right? This is something new that we created, this axiom of completeness. We said the real numbers are going to be an extension of the rational numbers that satisfy this new property being the axiom of completeness. And what that property says is that every non-empty bounded set has a least upper bound. So it's possible that by introducing this new property, somehow now the natural numbers don't have the property that we think. Maybe now there is some number that beats all the rational numbers. It could happen. And if you think that I'm talking crazy here, there are actually some extensions. So it is possible to start with the rational numbers and make an extension of them where there is a number that beats all the natural numbers. So that crazy thing that I'm telling you may happen, doesn't happen with the real numbers, of course, but it may happen with another extension of the rational numbers. So it's not such a crazy thing to think about if it can happen, right? So that means we should actually prove it. And this is important, and it's going to be later on a tool for us to show all kinds of infimums and supremums. We should be now be able to do them in an easy way. All right. So here's how we can prove this. Proof. And again, I'll tell you how the second one follows from the first. That's easy. But let's first go over property 1. Why is this true? How can we do it? Well, suppose not. So let's suppose it doesn't happen, right? So if this doesn't happen, it would mean that there is some x such that all the natural numbers are smaller than x. Suppose 1 is false. That is, there is x, a real number, such that n is less than or equal x for all n. That's crazy, right? So there's a real number that beats all the natural numbers. There's a real number that is bigger than all the natural numbers. Okay, well, that would mean that the natural numbers are bounded, right? Because that's an upper bound. This implies that n, the set of natural numbers, is bounded. And it's obviously non-empty. So then we can talk about its supremum, right? If it's bounded and non-empty, then it has a supremum. Then and I'm gonna just do it as the book. I don't know why they call it alpha, but I'm gonna use the same nomenclature as the book. So let's suppose that alpha is the supremum of the natural numbers, right? So that means this is a number, the least of the upper bounds. Okay, so then what? Well, let's consider alpha minus 1. So if we take away 1, that number is smaller than alpha. Of course, right? We're subtracting 1 unit. And because it's smaller than alpha, then it cannot be an upper bound, right? Because if it were an upper bound, it would be smaller than the least upper bound. Hence, alpha minus 1 is not an upper bound of the natural numbers. And if it's not an upper bound of the natural numbers, that means there is some natural number that is bigger than alpha minus 1. Hence, there is some natural number little n such that alpha minus 1 alpha minus 1 is smaller than n, right? So this guy is not an upper bound. It means there's someone that is to the right of it. But then, if I add 1 to this, it tells me that alpha is less than n plus 1. Okay, and this doesn't make any sense, right? Because what was alpha in the first place? We have it right here. Alpha was supposed to be the supremum of the natural numbers, right? Meaning it's a number that beats every natural number. It's bigger than any natural number. But look here, this n plus 1 is a natural number, and alpha is supposed to be bigger than all of them, and this doesn't happen, right? That's a contradiction. This is a contradiction because alpha was supposed to be bigger than every natural number. Right? So we got a contradiction. That means our supposition that this is false is wrong. So then that means 1 is actually true. Hence, given x, hence 1 is true. I'm going to just say. Okay. And then what about the second part?
Professor,
say it again.
before you continue, I have a quick question.
Yeah.
So you're saying that because alpha is the supremum, that this is false. Is that because we stated in our initial assumption that there is an x in the real numbers such that little n is less than or equal to x?
Yes.
Okay.
Exactly. Right? Because this makes the natural numbers bounded, and once they are bounded, we can talk about the supremum. If the natural numbers are not bounded, then you cannot define the supremum, right?
I guess I'm a little confused because when you say the supremum, I think the least upper bound. So I'm thinking there are upper bounds that can be bigger than it.
Yes. Yes, exactly. So that's what we're, yeah, I mean, this seems weird because this is obviously wrong. Right? I mean, the natural numbers don't have an upper bound.
Yeah.
So that's why this feels weird, right?
But it's not because of little n, right? Because little n is in the natural numbers.
Yes.
Okay.
Mm-hmm.
Thank you.
Okay. And then for the second part, well, if you can find a natural number as big, you can get the second one by simply dividing by n both sides, right? So you apply it to one of, okay, let's give a little bit of detail here. So for the second part, so you pick a positive real number, consider 1 over y. I can do it because y is positive, so I can look at 1 over y. Then I can use property 1 with this x. By property 1, there is n such that n is bigger than x. But what is x? X is 1 over y. And then if you just multiply by y and divide by n, this tells you that y is bigger than 1 over n. And that's the end of my proof. All right, so property 2 follows directly from property 1. Okay. All right. And but now we can actually properly show things that we couldn't do before about the supremums or the infimums, right? Let me actually, I want to do one of them at least, because we didn't, we let that pending. So, for example, you may remember this example that we did before. So it's example. We looked at this, a very simple set, the set of 1 over n. And we said that the supremum is 1. That was easy. And we said that the infimum is 0, but we didn't prove it completely. So now I want to prove it completely. Why is the infimum 0? So proof of infimum of A equals 0. Here's what you need to do. You need to do two things. You need to argue that 0 is a lower bound. That's easy because 0 is less than 1 over n, obviously, right? This is a positive number. So 0 is a lower bound. And then the next thing that I need to show is that it is the greatest of the lower bounds, right? The maximum of all the lower bounds. We need to argue that, right? So now pick another lower bound. Let L be a lower bound of A. So pick an arbitrary lower bound of A. And I want to show that L is smaller than 0, right? Smaller than or equal to 0. So let's suppose not. Suppose L is greater than 0. Okay. If L is greater than 0, then we can use the property, let me put it on the screen, the one we just proved, this one over here, this property. If you have a positive number, you can find an 1 over n that is smaller than that number. Okay? So let's use it here. So by Archimedean property, there is some little n such that 1 over n is less than y. Oh, not y, good call. We're using it with L, right? 1 over n is less than L. Okay. But wait a second. That seems fishy because didn't we say that L was a lower bound? Being a lower bound means that it is smaller than all of these numbers. And suddenly L is bigger than one of those, right? That's a contradiction. This contradicts the fact that L is a lower bound of A. And because we get a contradiction to what? To this, they are only supposition that L is greater than 0, right? So therefore, L is not greater than 0. Hence, L is less than or equal to 0. And then we're done, because 0 is a lower bound, and it's greater than all the other lower bounds. Thus, 0 is the greatest lower bound of A. In other words, 0 is the infimum of A. Okay, and now we have the complete argument there that we didn't have before. All right. Good. Here's another important consequence, and it is this next theorem, theorem 1.4.3, another consequence of completeness, and this is called the density of the rational numbers inside the real numbers, density of Q in R. And this is what it says. It says for every two real numbers, A comma B, say with A less than B, there is some rational number such that it's in between them. Right? That's what we mean by dense. Dense in that sense, that if you pick arbitrary two real numbers, so if you pick, here's the real line, and you give me any two numbers, A and B, then I can find a rational number in between. There has to be some R right there in between. Okay, so how do we do this? Well, it's actually a little bit, it's very easy. All we need to do is pick the right denominator, find the denominator of this R, right? Like, say I ask you, I mean, let's think about this. How would you do it in general? If I mean, in particular, if I were to give you some numbers, like say, I give you these two real numbers. Some number over here is, let's try pi, right? And then maybe this other number, which is 3.14159, which, by the way, is not irrational, right? That was in quiz number 1. This is a rational number, right? 3.14159. Because you can write it as that number divided by, so this is the same as 3.14159 divided by 1, 2, 3, 4, 5 zeros here, by 100,000. Okay, so let's say that you wanted to find a rational number in between these two. How would you do it? Well, you would like to know how close these two numbers are, right? So this pi over here is about what? Pi is about 3.14159.2653589793238462643883279502888, etc.
Do you know off the top of your head, pi?
Yeah.
Like all those digits? That's impressive.
Well, I only wrote this many. I don't know about 100.
Oh, wow.
But yeah, it's a nice number, right? Pi. Now the thing is, so I picked two that are really close, right? So how are we gonna pick it? Well, let's see. So how close are these two? Well, they match the first 1, 2, 3, 4, 5 decimal digits, right? And they failed on the next one. This one is a 2 right here. right here, we have a 2, right? And over here, there's no 2. So the distance, so actually my picture is wrong, right? And this is on the left of that. So let me fix it. Let me add another one here. Let me put a 3 here. Okay, so this one has a 2, this one has a 3, right? So that means that the distance between these two is less than, for sure, if we go to the next digit. So this distance is tiny, is less than 0.00. I go 1, 2, 3, 4, 5, 6, 7. That. Okay, that's I found the distance between those two, and then what I want to do is find out that this is a tiny number. I want a rational number that is even smaller than this, right? So a rational number that is even smaller than this would be like 1 over 10 to the 8, right? So if I use this as the denominator, for sure there's going to be fractions with this denominator in between here. That's the idea, right? Maybe I picked two numbers that are, so let's make my example a bit more manageable because I picked some crazy numbers here. Let's go back to some easier numbers. Like say you wanted to do it from 3.1 to 3.2, right? I simplified my example, right? How far apart are these two? Well, 1.1, that's 1/10, right? So then pick a denominator bigger than 10, right? Say 20. So I claim that between these two numbers, there's gonna be, so the distance, so that if you go by tenths, right? If you go by tenths, you go, here's 1/10 and here's the next one. Yeah, if I divide by tenths in this line, they will go like this. Here, and then here, and here, and here, and here, and here, right? These are all 1/10. So 1/10 are not enough because there's nobody with denominator 1/10 in between here. But if I use a smaller number, if I use 1/20, if I use 1/20, now from here to here is a 1/20, right? From here to here is 1/20, from here to here is 1/20, right? Now they're half as big. So now it works. I'm gonna find somewhere here where this distance is 1/20, and that one works. This is 3.15, right? That this is a rational number because this is 315 divided by 100. That is my rational number that falls in between these two. Okay, now let's do it in general. How would it work in general? Well, like we said, so b minus a is positive. So by Archimedean property, there is some number, little n, such that 1/n is smaller than b minus a, right? So there's a denominator that makes this number smaller than b minus a. And that's, so now I'm gonna show you that there has to be a rational number with this denominator between a and b. And how do I do that? Well, actually, we'll continue doing this next class because I will have to interrupt myself before I finish the argument, and I want to take more of your time today. So we'll continue from here on. So why is it then, what's going to be the rational number between a and b once we know this? Okay, we'll pick it up from then. Okay, so I'm going to stop right here. I want to remind you that we have the diagnostic test next class towards the end. And I will assign some homework next class as well to be handed out next week. Okay, so I'm just giving you a heads up right now.
So the homework's not due next class, it's due the class after that.
Yes. Yeah,
Thank you.
no problem. Any other questions before I sign off?
Homework will be on the topic that we're covering this week.
You mean the homework?
Yeah, the homework that you just said that's going to be handed in.
Yeah, I'm gonna pick one problem from 1.3 and one problem from 1.4.
Okay, got it.
Mm-hmm.
Thank you, Professor.
Good. All right.
Thank you.
Thank you for being patient with all these problems that we have. All right. See you guys next class.
All right.